So when we talk about enzyme kinetics, I want to first show you some slightly basic stuff. So this is our enzyme, and this is our substrate. And you all know that E plus S, this. Okay. So in this case, we need to say that the substrate is our independent variable and our enzyme is our dependent variable. And why? Because the enzyme is dependent on binding the substrate in order to work. So the velocity of the enzyme is dependent on the substrate concentration. And let me show you, when we talk about graphical relationships, we always have the dependent variable on the y-axis. So dependent, and the independent variable here. So say we had a relationship where if you increase the independent variable by a magnitude of 1, say, or 2, or 3, or 4, you get a corresponding equal increase. So if I increase the independent variable by 3, the dependent variable goes up by 3. If I increase the independent variable by 5, the dependent variable should also increase by 5. Now, if the dependent variable wasn't really dependent on the independent variable, we would have a horizontal line. But in the case of enzyme kinetics, we actually have, if you plot the concentration of our substrate and the enzyme velocity, or the speed at which it works, you're going to get this kind of curve. And let me explain more on the next page. So once you have an enzyme that's free and the substrate comes and binds to it, there's an enzyme substrate complex, which means that the enzyme is not free to bind another substrate. So that's why if you increase the substrate as you increase it, the velocity doesn't increase by the same magnitude. There's an initial slope like this, and then it flatlines. That flatlining is reflective of saturation, which means that all the possible enzymes are already bound. So you have most of them in this form, and no matter how much you, at that point, no matter how much you increase the substrate concentration, the velocity is not going to change because there are no enzymes to take up those substrates that you're flooding it with. So the velocity at which this flatlines is called Vmax. And I'm going to introduce to you an equation. And I just want to also give this a name. Our graphical depiction of velocity and substrate concentration is called Michaelis-Mentin Kinetics. Now our Michaelis-Mentin equation is this. And I'm just going to show you something. It just so happens, if you rearrange this, that Km equals to S at V0 equals to half E max. So what this is saying is that our Km, so the Km is the substrate concentration at half of the Vmax, and you trace it out on the curve. So what does Km mean? And other than being the substrate concentration at half Vmax. If you have a really low Km, so say it's low, relatively low, it's close to 0. That means that at a very low substrate concentration, so what a low Km means is that even though the substrate is scarce, the enzyme is still binding the substrate and working at half the maximum. A high Km means that the substrate needs to be raised really high in order for this to happen, the E to bind the S and work at half times maximum. And if you read between the lines of what I've written, you can conclude that at a low Km, this is going to be a high affinity interaction because substrate is scarce and enzyme is somehow able to bind it and then work at half times the maximum velocity. A high Km, you have to flood the enzymes with lots of substrate. That means that this is a weak affinity. And that ends my video on Michaelis-Mentin Kinetics.